Today I want to show you how we can use the net change theorem and integration to understand the rate of flow of blood to the brain. And we're going to use the net change theorem that we saw in a previous video. The idea here is we want to measure what's called the cerebral blood flow to the brain. But we can't measure that directly. We have to find a way to measure it indirectly. And so the experiment is as follows. A patient inhales air enriched with nitrous oxide. This nitrous oxide enters the brain through arteries and leaves through veins. So we call A of T the concentration in the arteries and V of T the concentration in the veins. So our goal, however, is to measure the blood flow to the brain, called the cerebral blood flow, and we call that F, and that's what's shown right here. Okay, so how do we get at this? Well, the trick here is that we're actually able to measure the amount of nitrous oxide that remains in the brain through magnetic resonance, or MRI. And so we're going to use that idea to try to tease out the value for F here. So our next step is just to talk about the inflow into the brain in a 10-minute experiment where the patient is inhaling this enriched air. And so the inflow will be F, the flow rate, times the integral from 0 to 10, that's 10 minutes, of the concentration, A of T dt. And so we're using the net change theorem to say that the net change coming in is an integral over the 10 minutes of the flow in, which is F times A. Equivalently, we can talk about the outflow in terms of the integral from 0 to 10 minutes of F times V. And that's what we have here. But notice, of course, because F is a constant in each of these formulas, we've pulled the F out from under the integration sign. So this is the amount of nitrous oxide that goes into the brain over the 10-minute experiment. And this is the amount that leaves the brain over a 10-minute experiment. Well, if after 10 minutes we can measure the amount of nitrous oxide in the brain, we call that Q10, then the amount that's in the brain after 10 minutes is the amount that came in minus the amount that left. And so the inflow given here is right here, and the outflow given here is right here. And we are using the fact that the difference of two integrals is the integral of the difference. And so we've got F times the integral from 0 to 10 minutes. This is the concentration of the blood coming in the arterioles, and this is the concentration in the veins or venules. And so each of these functions, A and V, have a particular form, and I've drawn them out here. And so this top curve here is A of T, and the bottom curve is V of T. Now, if we look at A minus V, and we integrate from 0 to 10, what we're really doing is we're taking the area given right here in the graph. And so this quantity right here is given with the shading right there. And so I'll put that in. This is the integral from 0 to 10, A of T minus V of T dt. Okay, so we need formulas, however, for A and V. And so A has the formula 0.04 T over 0.5 plus T, and V has the formula 0.04 T over 2 plus T plus 0.0002 T. Okay, so now we have the formulas. We should be able to compute the area given with the shading there. And finally, if we know this area here and we know Q10, then we can solve this for the flow rate f. So taking this equation, that Q10 is equal to f times the integral, we rearrange it to solve for f. And so now f is going to be Q10 divided by the integral from 0 to 10 a of t minus v of t dt. And so now at this point, what remains in calculating f is to calculate the area shown with the shading right here. And that's what we'll do next. Okay, let's go ahead and calculate that integral. So it's the integral from 0 to 10 a of t minus v of t dt. And that's going to be equal to the integral from 0 to 10. And we have 0.04 t over 0.5 plus t minus 0.04 t over 2 plus t minus 0.0002 t. This is all dt. This term here is the a of t, and these parts here are the minus v of t. And so we can break this into three components. The first is the integral from 0 to 10, 0.04 t over 0.5 plus t dt. And then the second is minus integral from 0 to 10, 0.04 t over 2 plus t dt. And then the third component is minus integral from 0 to 10, 0.0002 t dt. And so we want to calculate each of these. I'm just going to focus on the first one here and show you how we can go ahead and do it. And I'm going to use integration by substitution. And so we're going to consider the following quantity. We're going to pull out the 0.04 integral from 0 to 10 t over a half plus t dt. And now we want to think about how we want to do this calculation. We can use substitution. So if we set u to be 0.5 plus t, then du is equal to dt. Also, we can write t is equal to u minus 0.5. So we want to look at the endpoints, though. If t is equal to 0, u is going to be 0.5, and if t is equal to 10, u is going to be equal to 10.5. And so we'll use this when we use the method of substitution for a definite integral. We'll put the 0.04 in there first, and now we'll go from 0.5, which is a lower endpoint of integration, to 10.5. This is the upper point of integration. We'll go u minus 0.5, and we'll put that over u du. And so you can see we're almost at a point where we can integrate this, but what we want to do is break this into two terms. And so this is going to be 0.04 integral from 0.5 to 10.5, 1 minus 0.5 over u du. And so now we can integrate term-wise. And so we'll continue on the next line here, 0.04. And the antiderivative of 1 is simply u. And then we can subtract off the antiderivative of 1 over u, which is a log of the absolute value of u. And now this is evaluated between u is equal to 0.5 and u is equal to 10.5. And so finally, we can expand this out. And so when we plug in 10.5, we're going to get 10.5 minus 0.5 times the log of 10.5. And then we're going to subtract off 0.5 minus 0.5 times the log of 0.5. And when we put that on the calculator, this turns out to be 0.3392. And so we have our quantity right here. This is 0.33. 9392. We can calculate these other quantities if we want to as well by a kind of a similar method. Try this for yourself. For this one, I get 0.1912, and then for this one, I get 0.01. And so if I take 0.3392, and then I subtract off 0.1912, and then I subtract off 0.01, I'm going to get that this is equal to 0.138. And so that's the value for the integral of a minus v. So what's left to be done is to put it all together and back into this formula that we see right here. And so we need two quantities. We need Q10, and in the particular experiment that we're thinking about, Q10 turned out to have a value of 60, and we also need the integral from 0 to 10, a of t minus v of t dt. In our particular scenario, it turns out to be 0.138. And so when we calculate f now, we have f is equal to Q10 over the integral from 0 to 10, a of t minus v of t dt, and that'll turn out to be 60 over 0.138. And when we put that on the calculator, we get that it turns out to be 434.8. And the units for this turn out to be milliliters per minute. Okay, so this is kind of a cool experimental setup where we're indirectly calculating the blood flow to the brain by measuring the concentration of the tracer, nitrous oxide, in both the blood going into the brain via A and the blood going out of the brain via B, as well as the amount that has been built up in the brain over 10 minutes via Q10. And so at the end of the day, then this gives us an idea of how quickly the blood flow is actually getting to the brain, which can then be used for clinical purposes.